You know, your phone, your computer, heck, even your coffee maker, they all have something incredible in common. Deep down inside, they're all run by billions and billions of tiny, invisible faucets. So today, we're going to pull back the curtain and find out exactly what those faucets are and how they make our entire modern world tick.
When you really get down to it, every single electronic device has to solve one fundamental problem. How in the world do you control lightning trapped in a wire? I mean, it's like trying to choreograph electricity itself. You have to be able to tell it precisely where to go, when to stop, and exactly how fast to move.
So you might think the answer is some super complicated machine, right? Well, nope. The real secret, the starting point for all of this, isn't a machine at all. It's a very special kind of material, a substance that we can actually tell how much electricity to let through.
Think of it like a traffic light for electricity. You have your conductors, like copper wire. That's a permanent green light. Current just flows, no questions asked. Then you have insulators, like rubber. That's a permanent red light. Current can't go anywhere. But the magic, the real game changer, happens with semiconductors. They aren't just on or off. They're more like a dimmer switch. We get fine-tuned control.
And that right there, that's the key word, control. A semiconductor isn't just on or off. We can tell it exactly how much electricity to let through at any given moment. That one ability is the secret sauce for all of modern electronics.
Okay, so we've got this incredible material. What's the first, simple, but really powerful thing we can build with it? Well, we can create an electronic one-way street, a way to finally start telling all those electrons exactly which direction to travel.
And here it is. This little guy is called a PN junction diode. Now I know, it might not look like much, but trust me, this is our very first real tool for bringing some order to the chaos of an electrical current.
The easiest way to think about it, it's like a bouncer at a club, but for electrons. If the electrons are flowing in the right direction, hey, the bouncer lets them right through. But if they try to turn around and go the wrong way, nope, the velvet rope goes up, access denied.
So, to recap, its job is super simple, but super important. Let the current flow forward, but slam the door shut if it tries to go backward. This simple one-way gate is our first fundamental level of control.
A one-way street is awesome, a great start. But to build the world we live in today, we need something even more powerful. We don't just need a gatekeeper, we need a faucet, a valve that we can turn on, turn off, and adjust with unbelievable precision.
So take a look here. On the left, that's what it looks like in a circuit diagram. Super simple, right? But on the right, that's where you see its true power. That graph shows how a tiny little change to the input signal can create a huge, perfectly mirrored change in the output.
And this is the transistor. And it's arguably the most important invention of the 20th century because it has these two incredible superpowers. It can work as a lightning-fast switch, and it can work as an amplifier, making weak signals powerful.
So how does that whole faucet thing work for amplification? Well, imagine you're trying to control a massive fire hydrant, but you're only using your pinky finger to turn the valve. Your tiny, small action is precisely controlling a huge, powerful gush of water. The transistor does the exact same thing, but with electricity. It takes a small signal and uses it to shape a much bigger one into a perfect, stronger copy.
And this is what's so cool about it, this dual personality. If you just slam the faucet all the way on or all the way off, bam, you've got a switch. That's the ones and zeros of all digital computing. But if you're careful and you control the flow in that space in between, that's when it becomes an amplifier, the heart of all radio and audio tech.
All right, so now we have our building blocks. We've got the one-way street, the diode, and we've got the super precise faucet, the transistor. So what happens when you don't just use one, but you start cramming millions or even billions of them onto a tiny little chip? Well, you get something that looks like this. And hey, don't worry about understanding every little line here. The point is just to see how those simple little parts can be wired together to create something insanely complex, with every single little transistor playing its part perfectly.
Okay, but why does any of this matter to you? Because these crazy-looking diagrams, they aren't just diagrams. They are the microprocessors, the brains, inside your computer. They're the memory chips in your phone. It is literally what is making the screen you're looking at right now light up.
When you boil it all down, it all comes back to this one simple idea. Every video you stream, every text you send,
Every single bit of data flying around the globe is being processed by billions and billions of these microscopic faucets, opening and closing faster than you can even blink.
You know, for the last 50, 60 years, the transistor has been the undisputed king, the engine of all our progress. But we're starting to push right up against the fundamental limits of physics. So the big question, the really exciting question, is what comes next? What's going to be the new tiny switch that defines the next 50 years of technology?